So before I get into determinants, I would like to go over differentiating a matrix. So when we differentiate a matrix, we simply differentiate every element in the matrix and similarly we do the same with the partial derivative of a matrix. And I'm going to give an example for this one. So if I have the partial, or if I want to take the partial derivative of a matrix B with respect to X, this is like doing the partial derivative, and I'm going to spell out the matrix B as X squared, XY, XZ, XY, YZ. Actually, this is Y squared, XZ, YZ, and Z squared. So I'm taking the partial derivative with respect to X. So I come here, X squared, that would be 2X, XY, again, I'm differentiating this with respect to X. That would be Y, XZ, that would be Z, XY, that would be Y, YZ would be 0, Y squared would be 0, XZ, that would be Z, YZ is a 0, and Z squared is a 0. In structural analysis, we have, for example, the strained energy in a bar may be represented by U, where U is equal to 1/2 multiplied by a row matrix X and Y. So this is a bar element multiplied by a matrix A 2 by 2 multiplied by the column matrix of X and Y. Now this is known as the quadratic form. Because if I expand this, I can write it as U equal to 1/2 A11 X squared plus 2 A12 XY plus A22 Y squared. So that's why it's known as the quadratic form. Now, if I take the partial derivative of U with respect to X, that would give me A11 X plus A12 Y. The partial derivative of U with respect to Y, that would give me A12 Y plus A22, A12, this is X, I'm sorry. A12X, and A22Y. I can express this in matrix form as du by dx and du by dy is equal to A11, A12, A12, A22 multiplied by x and y. In a general form, where u is equal to 1/2 the transpose of the column matrix X, where X could be 2D, 3D, so I take the transpose, multiplied by a matrix A, multiplied by the column matrix X, du with respect to dxi is equal to the matrix A multiplied by x, where xi denotes x and y in this case, and A is a symmetric matrix. And you're going to see that more when we do chapter 2.
The top U, that should be the A matrix when you first find U. That's A11, A12, that's A12, right? Not 21.
On the bottom,
sorry, the first A matrix you define.
The first A matrix, A11, A12, yeah, and A21.
Or the one above that. Is it
here?
Yeah, is that 1, 2 or 2, 1 there?
1, 2, right? And
Right.
2, 1, but it's a symmetric.
So they're the same thing. Okay, gotcha.
This is not 2, 2, A21.
Second row first.
Yep. Anyone still writing? Good. Next, we're going to take a look at integrating a matrix. So as in matrix differentiation, we integrate every element. In the finite element formulation, of equations, you're going to see the form, the double integral of x transpose multiplied by a multiplied by x dx dy. And this is going to a limited integration and will yield a scalar. Now, again, this is known as the quadratic form. A has to be symmetric. So even if I go to a 3 by 3, if I look at A, so I have diagonal members 9, 8, 5, numerical example here. And then if I have a 2, I'll have a 2 here. If I have a 3, we'll have a 3 here. If I have a 0 here, I will have a 0 here. So that's a symmetric square matrix. And if I go for the X matrix, if this is 3 by 3, X is going to be 3 by 1. So I have like X1, X2, and X3. If I look at the quadratic form, X transpose times A times X, this will give us 9x1 squared plus 4x1 x2 plus 6x1 x3 plus 8x2 squared plus 5x3 squared. So you see where the quadratic form comes from. And again, this is a scalar quantity.
The last two terms.
Yeah, 8x2 squared plus 5x3 squared. You're welcome. Next, we want to get into determinants. The determinant of a square matrix. So we took the determinants for square matrices. Is a single number or a scalar quantity. The symbol of a determinant is either determinant of the square matrix A, or I can use the vertical bars and write it as these are the two vertical bars and put the matrix A between them. It means the determinant of the matrix A. Sometimes if we know A represent a matrix, I can simply put the vertical bars and A in between. The determinants of a 2 by 2 or a 3 by 3 matrices are usually calculated by procedures which involve or employ summing products of diagonals and taking differences. as in if I want to find the determinant of a 2 by 2 matrix, this is like the determinant of the elements A11, A12, A21, A22. This is equal to the product of the first diagonal, A11 times A22, minus A12 times A21. The diagonal method works only for a 2 by 2 or a 3 by 3 matrices. For higher order determinants, we can use Laplace expansion formula. Described in terms of cofactors, and that would lead us to our next topics. Cofactors, and I'm going to call that Cij. In order to get to cofactors, I would like first to introduce minors. So first, we will introduce minors to know where we're heading. A minor that I'm going to give here the symbol M, Ij, of a square matrix. So Mij, and of course that represents an element, is equal to the determinant of a matrix D with the row I and j deleted. So for example, if D is equal to D11, D12, D13, D21, D22, D23, D31, D32, D33. If I'm trying to find M11, I will delete the first row. I'm sorry, I said row I, and I forgot to say here, and column J, deleted, right? Not row I and row J, right? So I would delete row 1 and column 1. And then I'm really finding the determinant of D22, D23, D32, and D33. So if the matrix D is M by M, there are M squared MIJs, or M squared minors, one for each element of D. Now we can go and define the cofactor. And for the cofactor, I'm going to use the Cij of a square matrix. And I can say that Cij is equal to -1 raised to the power I plus j multiplied by Mij by the minor. So for an n by n matrix, there are n squares cofactors. One for each element. Each cofactor is a determinant of the minor, which was n-1 by n-1. If we can calculate all the cofactors for a matrix, we can assemble the cofactor matrix. So this is this matrix C. And it is a matrix of cofactors Cij. So this C cofactor matrix can be written as C11, C12, C13, C21, C22, 23, C31, C32, and C33. Comes from, if you look here, if this was an n by n, the determinant, the order of the determinant is 1 less the order of the matrix. So if the matrix was 3 by 3, the determinant is 2 by 2. You got it? We can do a quick example. If we have a matrix A that is equal to 1, 2, 3, 5, 2, 1, 6, 1, 3. Let's find the cofactor matrix C. So I'm going to start by finding the cofactors. So I have here C11 is equal to minus 1 raised to the power 1 plus 1. That will give me a positive sign, right? Multiply by the determinant. And this is the 3 by 3. The determinant is going to be 2 by 2. 2, 1, 1, 3. This is equal to minus 1 squared multiplied by 2 times 3 minus 1 times 1. 6 minus 1 is 5 times 1, so I get 5. C 2, 1. So I'm jumping here. So I have a minus 1 raised to the power 2 plus 1. So I get a negative here. Multiply by the determinant. And if I'm looking at this, I'm crossing the column and the row. Right? So I end up with 2, 3, 1, 3. Right? So this is multiplied by the determinant of 2, 3, and 1, 3. This is equal to a minus 1 raised to the power 3, right? Which is a minus 1, multiplied by 2 times 3 minus 3 times 1. So I get a 6 minus 3 times minus 1. So this is a minus 3. Let's pick the very last element. So if I do like C3, 3, I have minus 1 raised to the power 3 plus 3, multiply by, I'm going to cross the row and the column. So I have 1, 2, 5, 2. This is equal to a plus 1 multiplied by 1 times 2 minus 2 times 5. So I get 2 minus 10, that's a minus 8. And so on. When I continue, I can assemble a cofactor matrix C, and this will look like this. The ones we've calculated, I have here 5. I have here a minus 3. I have here a minus 8. And if you continue to do that, I'll get a minus 9, a minus 7, a minus 15, an 11, a minus 4, and a 14. While we are at this, let's also define the adjoint matrix. The adjoint matrix is the transpose of C. So I can write it as adjoint matrix of A is equal to C transpose. So in this case, if this is A, and I want to find the adjoint matrix, this is going to be equal to 5 minus 9 minus 7 minus 3 minus 15 and 11 minus 4, 14, and minus 8. I transposed the cofactor matrix. I mentioned the Laplace expansion formula. To get the determinant of a matrix. Of course, or simply finding the absolute, the determinant of A. How does this work? We pick any row or column of the matrix A and its corresponding row or column of the cofactor matrix C. We calculate the sum of products of the row of A and corresponding row of C. That sum is the determinant of A. So for example, the determinant of A, and I'm going to write it in a different way so you get used to it, is equal to let's do it symbolic first. If I have a matrix and this is like the cofactor matrix, I'm going to use, for example, the first row in the cofactor matrix and in the matrix A. So that would be A11 multiplied by C11 plus A12 times C12 plus A13 times C13. Or I can pick, for example, the second column. So, or I can find the determinant of A by picking the second column and say like A12 times C12 plus A22 times C22 plus A32 times C32. If I look at the previous numerical example, to get some numbers. We can find the determinant of A. This is A and this is C. So I can come here and do like 1 times 5 plus 2 times minus 9 plus 3 times minus 7. And when I do the math, I got minus 34. If I use the second column, I can go like 2 times minus 9 plus 2 times minus 15 plus 1 times 14. And I also get a minus 34. and so on. Even if we pick like the third row, you're going to get the same results. So if we go like the determinant of 8, and I pick this third row and the corresponding. So I would be going like 6 times -4 plus 1 times 14 plus 3 times -8 still is equal to -34. In index notation, we can say that the determinant of A is equal to the sum from j equals 1 to n of aij multiplied by cij, where I is for any row number. Or the determinant of A is equal to the sum from j equal 1 to n, and this time I'm going to pick any column number. So I'm going to go A ji times cji. This would imply any column number where I takes values less than or greater than 1. I'm sorry, greater than or equal to 1 and less than or equal to n, which is the number of rows or columns, because it's a square matrix. Some notes on determinants. Number 1, the determinant of A is equal to the determinant of the transpose of A. The determinant of the product of two matrices, A times B, is equal to the determinant of A multiplied by the determinant of B. The determinant of the inverse of A is equal to the inverse of determinant of A, which I can also write it as the determinant of A raised to the power -1. Number 4, if you interchange any two rows or two columns in the matrix A, the determinant of A changes its signs. Its signs. 5. if all elements of a row or a column of a matrix A are zeros, then the determinant of A is going to be equal to 0. Likewise, if two rows or two columns of A are identical, the determinant of A is 0. Number 7, if you add a multiple of one row of course, or one column to another row or column, the determinant is unchanged. The determinant of A is unchanged. And finally, if the determinant of A is equal to 0, then the matrix A is said to be singular. And you're going to learn in the finite element method that the global stiffness matrix is a singular matrix. And a singular matrix does not have an inverse. And that's why we cannot solve the stiffness equations until we apply boundary conditions. When we apply the boundary conditions or the supports condition, then there is a solution. But prior to that, we have no solution, or we have rigid body motion. And that's always one of the cases where when you are trying to run a commercial software package, if you do not have enough support conditions, you may get an error because there is no solution. You run into this rigid body motion scenario. Let me then move into methods of solving linear algebraic equations. Obviously, there are several methods to solve algebraic simultaneous equations, but some of these methods works well for small sets, like the ones we're going to be doing by hand of equations, solved longhand. While others are well suited for computer applications. And for large sets. So the first one we're going to look at would be the Kramer's rule. And this is suitable for longhand solution of small sets. So a set of algebraic simultaneous equations in matrix form may be described by A, the matrix of coefficients, multiplied by X, the unknowns, equal to C. I can also express this set using index notation. So this is using, of course, matrices. Using index notation, I can write it as the sum from I equal 1 to n of Aij multiplied by Xj is equal to C. So the Kramer rule will provide a solution that X I is equal to the determinant of the matrix Di divided by the determinant of the matrix A, where this Di matrix is the matrix A with column I replaced by the column matrix C. So this is C here. This method takes large amount of computer time, of course, for large sets. And is not suited for large systems. But of course, by hand, for small systems, it's really very easy to apply. And just for the sake of time, I would like to refer you to page 846 in your textbook. We have here a good example where we are looking at set of simultaneous equations. and they start solving for x1, so they replaced column 1 of the matrix with column 1 is replaced by the C column matrix, and we find the determinant, and we divide by the determinant of the matrix A. The determinant of matrix A is found to be -10. So you will notice in every step for x1, x2, and x3, I'm dividing by -10, but I'm changing the column corresponding to the unknown that I'm trying to solve for. So that's why understanding determinants was useful, because I can use the Kramer's method to solve for x1, x2, x3, or variables for a small set of algebraic simultaneous equations. Okay. Any questions about this method?
The index method, or the index notation, it's the sum of aij times xj, and is that equal to c with j?
I'm gonna put C. Oh, yeah. Here when I expressed it in matrix notation, that would be CI. Yeah. Actually, the more I think about it, so this is how it's written in the textbook. Yeah, I think it should be from j equal 1 to n, right? Because it would be like a11 times x1 plus a12 times x2 and so on, and this would remain CI. So I think this should be j equal 1 to n. Next, we're going to look at inversion of coefficient matrix. Yeah, sorry. Where if our set of equations is described in matrix form as AX is equal to C, if I can find the inverse of A times A multiplied by A times X is equal to the inverse of A multiplied by C, then this will give me the solution for X. I get X is equal to A minus 1 times C. Now, the question will come then, how do we invert A? So of course, there are tons of computer methods, but we're trying to learn where these are based on. To invert A, we can use the cofactor method or row reduction. In the cofactor method, we can use the adjoint matrix. So the direct adjoint method will give us A minus 1 is equal to the cofactor matrix transposed, which is the adjoint matrix, divided by the determinant of A. So as you can see that this is equal to the adjoint. So this, you can see how we can call it the cofactor method or the adjoint method. The adjoint of the matrix A divided by the determinant of the matrix A. And I'm trying to mix notation to get used to it. So for example, if we want to find the inverse of A, and A is equal to a 2 by 2, where I just have 1, 4, 3, and 2. The cofactor matrix is equal to two minus 3 minus 4 and 1. Can you all follow how I got this? The determinant corresponding to each element, right? So for 1, I get a 2. Here, I have a 3, but it's raised minus 1 to the power 2 plus 1. Here, I have the 4, again, times minus 1 raised to the power 3. So I got a minus 4, and so on. Now, the determinant of A is equal to 1 times 2 minus 4 times 3, which is equal to minus 10. Therefore, if I apply the direct adjoint method, the inverse of A is equal to, I take the transpose of the cofactor matrix or the adjoint matrix, which would be the C transpose transpose C, right?
Yes. We just got C now, we didn't transpose it.
I just got C.
But we didn't transpose it.
Hmm?
But we didn't transpose it.
We did not transpose it.
Yes.
Right. So if we want to transpose C, I should get 2 and minus 3 and minus 4 and 1. And we should divide this by minus 10.
Based on the formula.
Based on the formula. So this will give us a minus 2, a 4, a minus 0.2, a plus 0.4, a minus 0.3, and this will be a plus, and a minus 0.1.
That's based on your formula of tensor.
Based on the formula that the inverse is equal to the C transpose or the adjoint matrix divided by A. Okay. Now, this inversion method is practical only for small systems. And is used during the formulation of the finite element equations. And it is in particular useful if you have multiple loads. So for example, if I can write my global stiffness equations as K times D equal to F. Where F here is one column matrix. Imagine if I have multiple Fs. If I can write it as K for multiple load cases equal to F, if I can find the inverse of K, and I have the same boundary conditions, right? So then we can quickly, actually this will become now D, a matrix like this. So if I can find the inverse of K, then we can solve D for the multiple cases of loading directly. So F, single load case, F are multiple cases of loading. D is displacement corresponding to one load case. While D, which is going to be equal to like D1, D2, D3, and so on, will give us like each of these is like a column matrix. So these are displacements corresponding to multiple load cases, as in F1, F2, and so on. So this could be another advantage of finding the inverse. As you're going to see, when we are working on large system, sometimes there are many zeros, and we call it that the matrix is sparse, and it is also banded. So sparsity and banded nature of the stiffness matrix can be used to the advantage in terms of storage requirements. Next, we want to touch on an elimination method. So the Gaussian elimination method. This is based on the triangularization of the coefficient matrix A. So in the system of equation, we have A times X is equal to C. So the first step, I remember we talked about upper triangular matrix and lower triangular matrix. So in this case, we want to have an upper triangular matrix. So we want to eliminate the coefficients of x1 in every equation except the first one. So really we are selecting in the first step, select A11 as a pivot and add the multiple of minus A12, I'm sorry, A21, so the coefficient of x1 in the second equation, divided by A11 of the first row to the second row.
Sorry, what does that say?
Yeah, add the multiple of the negative of A21 divided by A11 of the first row to the second row. So in doing so, I will make the coefficient of x1 in the second row become 0. And then I will add the multiple of minus an1 divided by a11 of the first row to the nth row.
Is it minus A?
an1. So basically, I'm gonna do that for each row below the first row. If I follow this procedure, I'm gonna end up with the first column in the A matrix, all 0 except A11, right? Then I'm gonna move to the second column. Now for the second column, my goal is to end up with a triangular, I say here triangularization. So if I'm looking at A, I really want to see a diagonal, coefficients at the top, but everywhere else, I want to see zeros. Something like this. Okay.
So your x2 will be pivots.
Excuse me?
So you make x2 the pivots.
The next step will make x to the pivot. Very good. Right. So in the next step, we're going to eliminate the coefficients of x2 in every equation below the second row. So we still have the coefficient here for the second row. So this was the first pivot. Now we're going to this. Oh, so this was the first pivot. Now we're going to the second pivot. So we are going to select A22 as the pivot. And we are going to add the multiple of, I'm going to move to the third row, right? So I'm going to have minus A32 divided by A22 of the second row to the third row. And I'm going to continue to every single row below, add the multiple of minus AN2 divided by A22 of the second row to the nth row. So after that, A33 is going to become the pivot and so on. So we're going to repeat the process until A becomes a triangular matrix. Just for the sake of the time, it's going to look like this. So A is going to become a triangular matrix. You see, we have a diagonal of A11, A22, A33, A44 until A and N. Multiply by the unknowns, and the constants are also changing because they're part of the rows. Okay. So this is the first iteration, second, third, and so on. So we're going to have n minus 1 times. Once I do that, if I take the last row, I can solve for xn, where xn is equal to c n minus 1 divided by the coefficient ann n minus 1. Because the first row we're not touching. So that's why it's n minus 1. And then we're going to move back and solve for all the others by back substitution. In your textbook, equation 315, explain this process in index forms, which is really well suited for a computer program, right? So when we have these loops, we can easily do it. Like there is the Gaussian elimination, there are other elimination methods like the Gauss-Jordan, like the Cholesky methods. And there is other general class methods that are used to solve system of linear equations known as the iterative methods, where in the iterative method, you start by assuming a solution. And you usually have a good start by taking the constant dividing by the coefficient of each row of the variable. And then you go back and substitute these in the equations. And you keep repeating, of course, it relies on using a computer, until your answer converges. Now, the quality of the solution depends on your starting point. That's why we say in the finite element method, a good starting point is by dividing the constant and the coefficient corresponding to each row. That's a good starting point. Okay, I think with this, you should be able to complete the quiz 1. It's going to be straightforward. You just have 10 questions. Just make sure you understand the topics of Appendix A and Appendix B for the most part. And then coming back this coming week, we should be able to start Chapter 2. Right. Thank you. Have a great weekend.
Is that? Do what?